Okay, so hello everyone, and firstly I want to welcome all the participants that join us here at this webinar. Good morning, good afternoon, and good evening, because we have participants from 36 countries today with us. And thank you all again for joining us here. We have very special guests today with us from the University of Salzburg, Dr. Stefan Lang, Dr. Florian Albrecht, and Gella Workineh. Thank you, Stefan, Florian, and Gella, for joining. Stefan is an associated professor at the Department of Geoinformatics and Vice Dean of the Faculty of Digital and Analytic Sciences at Paris-Lodron University of Salzburg. Florian Albrecht is research lecturer at the Climate Hazard and Risk Lab at the Department of Geoinformatics, again at the University of Salzburg. His research is focused on the design, development, and validation of Earth observation, derivative geographic information products for applications in natural hazards and urban planning. Gella is a Master of Science in Earth Observation and Geoinformatics Science. Currently, he is a doctorate student at the University of Salzburg, working on integration of deep learning models with high-resolution satellite images for humanitarian applications in emergency responses. And our plan for today is, as normally, pretty simple. Firstly, I will just do a very quick introduction of the CREODIAS platform with focus on the GPUs and other and all the tools and all the products we have for the AI and Earth observation. Then Stefan will introduce us to the artificial intelligence and application remote sensing. Thirdly, Florian will talk about AI processing of satellite data, how the land classification and urban heat. And finally, Gella will show us a technical demo how to implement AI code on a live model. And we'll conduct our session with summary and QA. If you have any questions, please ask them in the chat. We'll answer them in the QA session after the webinar. And all the presentations, recording, and all the answers to the Q&A will be sent to you after the webinar. So if you don't worry if you miss anything, you will have a chance to get back to it after the webinar. Firstly, CREODIAS, your cloud platform with GPU ready for AI deployment, application development. So CREODIAS is a DIAS which hosts Copernicus data and Earth observation data with available on-site processing. We add from 16 to 60 terabytes of new Earth observation data to our public repository daily, so the data is very much growing. And we focus on the data to be ready for immediate processing, so that you can use the data just online from DIAS to do the processing. There is no need to copy the data from the DIAS to your own repository, so you can process it on site. And it is very important, and this is very to have the data ready to be processed, because the Earth observation data is huge. So our public repository is almost 30 petabytes of data, which is very much, and even for very large projects, having that big repository is just way too much. And normally with processing of Earth observation data, users spend up to 80% of their time just to download and retrieve the data, not on the processing, not on the processing the data. So it is important for that on a CREODIAS you can do it almost instantly. You just don't have this waste time. And CREODIAS is there are three components of the CREODIAS. One is Earth observation data repository and data catalog, when you can search data and download it. There are public collections, there are private collections, there are search engines, and there are ways to access the data, which is what the users want when they want to access the very big data. There are multiple cloud services in multiple locations that you can process the data on compute, renting the compute power, or using Kubernetes, or using our processing as a service functions. And there are also tools for users that help to prototype, that help to process and to find the data that you want. And we try to enrich the service on a daily basis in a way that you can just get everything done faster, smoother, and prototype and do your calculations faster. This is the cloud platform oriented for Earth observation, but with focus on processing the data faster. And CloudFerro, which is the operator of the CREODIAS, is also a partner of NVIDIA. So you have all the tools through the CREODIAS, and through CloudFerro you have access to all NVIDIA tools and all NVIDIA process chains that you may need for your processing. So this is covered under you can use all their software when you rent the hardware and run the computing power from us. The computing power is quite simple, and the GPUs in the cloud this is a very simple offer, but it is one that is suitable for many applications. In our primary cloud, in CF2 Cloud, we have single VMs with single GPUs, or the server with 4 GPUs. So it is a small flavor for when you want to do the processing of the data or just to test some idea, and very, very big server with 4 GPUs when you need to train your model, which can process very big amounts of data. And on the WAF 3.1 cloud, we have in public server that you can use publicly VMs with virtual A6000 GPUs. They have up to 48 gigabytes of RAM on card, and also so you can start very small with very small 1/8 of the card, or you can go very big with very big card, that very big server. And on top of that, we have system images that are ready for processing. So you have all the drivers, everything that you have, all the tools that you need to just start the processing immediately. Run the VM, just upload your user key credentials and start processing immediately, not wasting time of setting the environment. And we try to expand this offer on a daily basis. So if you feel, or if you need any other tool that is lacking and it is not inside this standard tools, please let us know through the support. We try to enrich those system images, and we try to add new services daily. We also offer custom solutions on our platforms. So firstly, the servers with multiple GPUs. So our biggest servers are up to 8 A100 GPUs. We can also build system configurations for projects that last for a long time and add it to the public cloud, so you can use them. As I said, we can add tools to the ready-to-use system images. So you can be able to do everything faster and not be dependent and not have to be forced to build your own image. And in a month or two on WAF 3.1, we will add GPU support to the Kubernetes as a service. So you can be able to run the tools on the GPUs using our Kubernetes support. So running all the deployments will be even faster, because you could just run your pods and done. The data collections available on CREODIAS are very rich. So you have every Sentinel, Landsat, NVSat SMOS and MODIS collections, other Copernicus services like CAMS, SAMS, CLMS, SMES, DEMS, and so on. And also for users that require, we have VHR Imaginary, so you can order those through our Finder or through contact with our sales department, and then you can have access to those repositories for the parts of the data, and you will be able to process it the same way like all the data. And not all the collections are full, so some collections are limited, but again, if you reach out to us because you need full archive, or very old images, we can download them and add them to the archive. And some products are orderable, but orderable products means that you can order them through the API and process them as soon as they're available on the data. And just to summarize, you can see our data offer now, right, on our site, and you also have access to our tools that help you process your data. So you can access EO Finder to search the data. You have a cloud dashboard to set up the environment really easily. You have access to the third-party applications that are part of the DIAS, and you have access to the Jupyter notebooks to prototype and test something. If you think you need more tools or something is missing, please reach to us. We are always happy to enrich our tool chain. And I hope you will find the next presentation, the presentation from Stefan Lang on artificial intelligence, interesting. Stefan? Okay, a second. Oh, we can see you guys.
Yeah, okay, good afternoon. Thanks, Marcin, for the introduction. And I think it's wonderful sequence because, well, the title is GPU and AI, or GPU for AI and EO applications, and this is somehow also reflected in the sequence that we have here in this presentation. So we had the chance to listen to Marcin from CREODIAS about the infrastructure, actually, what is available. And then the second element is now AI, because this is actually the aim that we are using this infrastructure for, and then within EO applications, so basically in image analysis. And my task is now to zoom a little bit out and introduce a little bit the concept artificial intelligence in a broader sense, but then going, of course, into image analysis. And then we will further on go more into detail, have a little bit closer look in the applications. So this is, I think it fits perfectly also to the title. So obviously artificial intelligence is what it says. So there is two words, two parts, artificial and intelligence. So it's something that we use the aid of computers to support our human intelligence, and not only support, but actually try to simulate it. Yeah. Eventually to go beyond. We don't know where this development will go to in the future. Maybe this is something which is self-enforcing, so we cannot really control this. But for the time being, it's more the attempt to approximate to human, to mimic human reasoning and ultimately action by digital information assimilation and processing, as you can see here in this quote. So what is intelligence? Is something that where we use our senses, we use our knowledge in order to process information. So this interaction between senses and knowledge, I think, is quite important in our human capacity to perform intelligent decisions. And this is obviously something that we would like to transfer to the computer. So in the digital world, we have, well, it's sort of the same concept, even though we use different terms for it. So it's not the sensors, it's actually sensors, digital sensors, and we know that there's a lot of out there. And today we talk mainly about Earth observation sensors, basically satellite sensors. Then in the middle, we have the digital data processing, and knowledge, of course, we can also use in representation knowledge organizing systems. Yeah? So it's basically mimicking this sort of broad concept of how human intelligence processing is being done. Next slide. I think we can proceed ourselves. Yeah, okay, good. So it's I think important to notice and to emphasize that artificial intelligence, it's not an invention of the last 2 or 3 years or a couple of years, even though the hype around machine learning has significantly increased over the last recent years, and there is now new study programs coming up. Also here, for example, at our faculty, Digital Analytical Sciences, we are offering artificial intelligence courses, but of course, well, we come more from the geoinformatics point of view. So there's sort of convergence of all kinds of technologies. Altogether, AI, artificial intelligence, has a long tradition, more than 50 years, especially also in image processing. From the first Landsat image that has been recorded in the early 70s, we have the concept of digital image classification, which by and large are still the same. It's the conversion of reflectance values into meaningful information. So this has not changed at all. So the general concept is the same for several decades. Obviously, there is something new. Otherwise, we would not sit here, and otherwise we would not need GPUs. We would not talk about this massive requirement of processing power in computers that nowadays we can realize with GPUs. So there must have been some changes, and it's basically the realization of neural networks. Again, the models of the brains are not new at all. It's again something which has been come up in the late 80s or in the 80s of the previous century already. But the actual possibility to realize that is only nowadays possible. So machine learning is not the same as artificial intelligence. It's actually a sub area of artificial intelligence. We have other components like in computer vision or knowledge-based approaches that are not machine learning in the narrow sense, but well, this is at least the focus today. And whenever we have new things coming up or new paradigms, then of course there's always the attempt to merge this with more traditional approaches, and something that we have nowadays, or we have this term explainable AI or hybrid AI, where we try actually to bring together the traditional, more traditional physical model-based approaches and knowledge-based approaches into this machine learning. When we talk about machine learning and image analysis, then again, there is sort of a sub area which is called deep learning, as most of you hopefully probably know. So this is the notion of the capacity of a computer to process deep representations, and what that means exactly we will see in the next slide, of reality. So it's not just like a one-dimensional representation, an area of pixel, but it's actually something, a stack of, in this case, convolution layers that represent this sort of deep neural understanding of an image. How do they work, these neural networks? I mean, probably we're all aware of this general idea that we have sort of connected neurons, just as our human brain works, and there are certain layers and they interact with each other. And obviously, of course, if we connect each and every of these nodes, then we would have massive neurons and massive networks. So the question is how we can reduce this in meaningful ways. And one idea is actually to apply convolution, to apply processing steps that extract the meaningful parts of the image and leave aside the more details, and vice versa, and construct sort of meaningful layers and connect these rather than to do all the connections. This is basically how this looks like. I think most of you have seen this before. So we have this input layer, and then we have a series of hidden layers that are constructed around convolution layers, specific filters that applied here, and then we have an output layer where we reconstruct basically the scene and the output. So this is an advanced way of image classification. Again, what is image classification? In general, this has not been changed over the last 50 years. Conversion of input, which is the reflectance, which is an array of pixels, an image, and into an output. And actually what all the things that happens in our brain when we look at a picture like this, where we see the sunflowers and we see the sky in the back and the clouds, to represent this image understanding in a sort of coherent and comprehensive way in the computer. We know that this has advantages and disadvantages. So advantages is for sure the fact that we sort of we can pass the not the responsibility, but actually the task of image understanding to the computer, so the computer can learn itself. Of course, it has to be fed by us, and we do this by sampling, and then the computer can learn this and build the weights between the nodes, and then produces the outcome, and reinforce its learning also by circular approaches. But on the other hand, of course, the drawback is that we sometimes we consider neural networks or these models of neural networks as black boxes, because we cannot really understand, or we cannot really, it's not really transparent with what happens there. And therefore, the idea is that we actually combine this with other more transparent or knowledge-based approaches to be better conditioned in this entire process. In general, if you look at these convolution layers, then this could be, of course, in the spatial domain. I mean, this is probably the most obvious, that you have filters that you apply to one single scene, one single input scene, representing reality at one given point in time. But obviously, there's other approaches that also are able to analyze temporal stacks, so basically several time slices on top of each other, and applying similar techniques in representing these time stacks through different convolutions that then work over time. Yeah, and we will see later on a few examples. So I'm not going too much into detail with the architecture here, and because this will be explained more in depth a little later on. Just as well, concluding this part, so we have different tasks that we are actually fulfilling or try to fulfill in deep learning. So one is image recognition. I'm preferring this over image classification, because this is sometimes referred, as I said before, to the overall process of transforming reflectance values into information. This is broadly conceived as image classification. So image recognition would be basically to understand the scene content of an image. So this is an image of an airport, this is an image of a forest, and so on, even though we are not really delineating this. Then we have object detection, so basically trying to find out where objects are located in the image, even though we are not really delineating it exactly. Then we have semantic segmentation, which is basically now trying spatial explicitly to transform pixels into categories, into classes, and assigning class probabilities, and therefore having the chance to do like a spatial explicit classification. And then instance segmentation would be even one step further, where we try to extract and represent individual objects, and then we can do object counting and so on. Last but not least, and this is then the last slide, is just to, again shows the difference a little bit, or just highlights the difference between semantic segmentation, instance segmentation. These are sort of the flagships nowadays in image analysis, because this is quite important for the tasks that we are doing, because in the end we will have like a result where we can really do a full-scale representation. And especially if we work in geospatial context, it doesn't help if we just know that an image is about an airport, but we want to extract the airport. It's not enough that an image shows cars. We want to see where the cars actually are, and we want to turn this into geospatial information. So therefore, these segmentation-based approaches are most relevant. All right, with this, just in a nutshell, an introduction, I hand over now to my colleague, Dr. Albrecht, who will give you a little bit more insight about the capacity of AI in EO using a very specific example. Okay.
So hello, also from my side. I will continue Stefan's talk with a little bit more focus on the on a specific application and the workflow, and rather how the workflow has changed through using AI instead of previous classification methods. So AI processing of satellite data, that's the objective here, and we do that. This is the structure of my talk. So I first go into the potential of AI-based land cover classifications on EO clouds for analyzing urban heat islands. And then I analyze the remote sensing workflow to understand benefits of the EO cloud for deriving geospatial information. And we will have a summary about that workflow analysis. So urban heat islands. This is a picture of a Landsat scene from a couple of years ago of the city of Salzburg, where on the left side you can see the true color image, and on the other side you can see the true color image overlaid with the land surface temperature of the corresponding thermal band of Landsat. And so you can already see interrelations between the land cover and the temperature. So everything that's vegetation has cooler temperatures than the land cover. And so in that way, here it's a little bit more analyzed, focused on a specific district of Salzburg, where we mapped the land cover in only a couple of categories, 4 categories of built up vegetation, water, and shadow. So just to make sure that we can make a correlation on the building block level between the vegetation and the temperature. And basically what you want to do when analyzing urban heat islands is to focus on the built-up area. So urban areas worldwide are expanding and become denser. So that's one of the drivers of the couple. Like, I think it's more than 75% of people now living in cities, and that really increases. And the problem is that the denser built-up areas increase the local warming, and so we get the urban heat island effect. And that comes with certain problems in health, pollution, and other things. And so planners need geospatial information to mitigate negative impacts. So there it is. From Earth observation data, we want to gather information that can help us to act. And so in that way, what they want to have is they want to identify locally implementable countermeasures and monitor their effectiveness. So whatever, how planners need maps and need to make them in a way that they can use them to act, to monitor policies and so on. So urban areas, that's a land cover topic. It's globally applicable to all urban settlements, and it is a dynamic process. And all these 3 elements, and additionally the land surface temperature, they show us how this is really an Earth observation topic. So we have Earth observation data that provides time series information from satellite imagery. And so our task that we want to do now is to model and assess trends of evolution of land cover and land surface temperature on a local level. So ideally, we have the building block level, but it could be smaller as well. And so EO clouds are a good, really the perfect environment to process EO data, because they provide all this data and at one single point and enable us to do workflows differently than we used to do them before. So this used to be our process on a standalone computer. You search your image data, then you download it, set up your project, extract Earth observation information, validate it, and provide it to the user. So on an EO cloud, you don't need to do the download anymore. Yes, you search, but your search list goes directly into the software that you have there. And so you can set it up without having to download the data and manage data. And then on the EO cloud, you can use all these capacities, like Marcin illustrated at the beginning. You have large processing capacities available, and of course, storage space and memory for doing all these processes. And a further benefit is that you can share the data that you produce on the EO cloud. You can also share processors that you have developed on the EO cloud. And so this is a nice environment where many things come together that make it easier to process Earth observation data. So going a little bit more into detail when you want to do a classification, you have this workflow that you collect input data, then you select your classificator and the parameters, and you perform classification and assess the accuracy. And if you are happy with the accuracy, then you can go for further use. But it's always with the development of image classification that you try to improve your accuracy as good as possible. And we used to do that by not just focusing on the image data, but also using filters like NDVI and others like edge detection or low pass and high pass filters to improve the image data information and do the classification better. And here comes into play the machine learning and deep learning methods. Machine learning here, for example, random forest is such a classificator, requires an expert to identify and extract suitable classification features, those filters that I mentioned, as basis for setting up the model. And so you can see in the figure below that there is an expert involved in preparing the data for classification. And with deep learning, this is handed on. So if I go back once more, this filtering part is one thing where I want to start to explain how convolutional neural networks are different in approaching this. So this is the structure. Stefan introduced it. I want to go a little bit more into detail. So the basic structure is that you have an input layer, you have hidden layers, and then you have an output layer. And for getting from the input layer to the output layer, you have these nodes where you have all the connectors from other neurons, where you have weights and a bias and an activation function. So these are parameters that you have to set, or that the software, the process sets for you. And with the stepwise reduction of the size of a feature map, you get from an entire feature map through convolution and pooling to a single output. And in that way, it is this architecture is meant for looking at one piece of a image and say, yes, that's part of an airport or not. So you classify the entire snippet of that image. So setting up such a CNN is that you define the amount of hidden layers that you want to have. So you have an input layer, then you have 3 hidden layers in this example, and then you have an output layer. And with the number of neurons, you define the layers. And so convolution and pooling, those are the filtering techniques that are applied. They may not directly use an NDVI filter in producing that in there, but they produce that many, so many filters that somehow this is also covered and goes into detail there. So how does this algorithm work? You train the neural network in cycles. So the input data passes through the network, and then decision criteria for assigning pixels to classes are determined, which are these biases and weights. And then an image classification is predicted. And the classification results is compared with validation data, and errors are identified. So you use accuracy metrics in there. And if the learning process has become too small, like the accuracy level is not yet has achieved a certain threshold, then you you stop the process and you have your final result. If not yet, you have the error values. They are used to correct the decision criteria in the network, and this is the correction through the entire convolutional neural network. And then with corrected decision criteria available, they are used for the next cycle. And then you do another amount of cycles and end up with many cycles until your accuracy achieves the level that you want to have, and you have an improved classification. So what does this change from our workflow? So this iteration that we had for making a new filter and improving the classification by that, this is a principle that the computer adopts here. So you do accuracy assessment, you correct, you do the classification again, and you do that again and again and again. The filtering has been taken over by the computer as well, and the classificator, CNN, and the parameters, here you work with hyperparameters now. So you do not check the accuracy yourself, but you define the metric which accuracy you want to have, and you define how many cycles you want to have, or how much learning the computer has to do. And what also has changed is the way of the in situ survey. You have now 3 categories of data. So you have the training data and the test data that used to be as it is. And now the 90% of the training data are split into training data and validation data. So for these, this 70-20 is the information that the computer can use for the CNN network, and the other 10% of test data go into the final accuracy result to keep that separate. And then you can use the data in the end. So basically what has changed in the entire process when we have EU clouds and not anymore the local machine. So we can avoid unnecessary tasks like downloading data or reuse of already existing results. We can build on results here much easier. And we avoid duplicated storage of data, again, the downloads. And where possible, we replace subjective tasks with objective approaches. So we let the computer select classification features and not do that ourselves anymore. Using methods that allow handing on highly repetitive tasks to the computer is also one approach. And in that case, with CNN, we have a method that allows us to hand on this classification task to the computer and do that. So we let the computer do those further iterations for accuracy improvement. So this is the way how the EO Cloud makes our work mode and our usage of the infrastructure more efficient. For urban heat islands, this would mean that we get the possibility to do larger areas or even pushing towards that global coverage for built-up areas. And we can use other data in there, like the Landsat 8 and the Sentinel-3 data for focusing on on the land surface temperatures. We can use air quality measurements to combine that into the urban heat island topic, and climate and weather data is all available on the EO Cloud. Marcin showed us the ample amount of data that we can use for our processing on the CREODIAS platform. And so, yeah, that's it, where I want to end with this workflow analysis for cloud processing of EO data.
Okay, thank you very much, Florian, for your presentation. And now we will continue with technical demo, how to implement the iCode. And are we ready? Yeah, I think so.
Yeah, I'm ready. Can you stop your sharing?
Yes.
So the first thing is like accessing data from any sort of repository, and to do that, the usual way is like using specialized interfaces that are designed for the users, for example, a Sentinel Hub. And following that is a pre-processing step, and this also is depending on the task and user need, whether you are working on radar or you are working on optical, and again, it also depends on the type of activity, whether you are working on system testing or product testing or like generation of new product. And then after that, I put this pre-processing stuff into two, because normally when we are working on deep learning based EO analysis, the normal processing may be common, but after you pre-process the data should be converted into a model input-output structure, which I'm going to speak later. And that later on, now after pre-processing the data, what we do is we are setting the environment and creation of the model. And after we create a model and we train it, we optimize it, we validate it, and then when we are sure enough the model is working on our test data set, and then we again check its performance on test data set. And after that, if we are satisfied by the model performance, either we can deploy it in somewhere to work in automatic or semi-automatic way, or we can upscale it in a larger geographic region. So accessing the data, so normally it's common to access, like most of the time now the user community is using data which comes from Sentinel. And to use a Sentinel, the usual way is like using Sentinel Hub from like website. But if you are working on the command line interface, and if you want to have a single workflow in your computing environment, you can use Sentinel Python API, which is an integrated API that can enable you to access the data from the repository. And to do that, normally what is expected from you is first you register in the Sentinel Hub, and then you will have a password and a username. Using that, you can directly you can directly grab the data using Sentinel Python API. So using this API, you can do a summary of available data. You can screen, you can select by using many criteria existing in the package. And for example, after selecting specific data, for example, if you want to see how many data sets you have, if you say like products.key, it will give you this kind of a list of data sets with its key. For example, it tells me for a small steady site, I have 43 images. So again, as you can see from the code snippet, this package allows us specifically to select a specific product, a specific orbit type, the number of data we need, and the area, processing level, and the time. And this is like this code snippet can work like as a magic. And then after all, once you say api.download all, once you are sure you need this data, and the data will be in your local disk within, but it also depends on the network capacity you have. The other option is as it's presented by Florian and Martin. Now cloud providers are also come up with their technique where they can directly put the data which is from providers, and you can compute directly from the local storage. The other thing is if you are needing data out of Sentinel, and there is also a package which is more integrated with other providers, and like Solo, CREODIAS, Ondia, and this package is called Earth Observation Data Access Gateway, or EODAG. So the implementation is almost the same with Python, with the Sentinel API. And if you have an interest on it, you can see the link here, and as the link, you can also access directly from the link, and there is ample amount of documentation and user help on there, and the implementation is almost the same as Sentinel API. Once we see how we can access the data, and the second thing is its pre-processing. So for pre-processing, like the demo I'm going to show is I'm going to use like a radar image from Sentinel-1. So there is a specialized user interface or software built by ESA, which is called ESA Snap, which have an ample functionality or already like built-in functionality. So working on the software may be very nice, but sometimes it is routine. So if you want to integrate with your Python environment either in your Jupyter notebook or on your command interface, when you install the software, it asks you, do you need to integrate Snappy Pi in your system? And you can say yes, or if not, if you already have installed it, you can also integrate it later after the installation. Once you integrate the Snappy Pi with the ESA Snap, you can directly like use all the functionalities provided by ESA Snap in your Python command line interface or Python programming interface. As you can see from here, the only thing is like you can import Snappy Pi package, and the rest is almost very easy and straightforward, and you can use built-in functions as any Python package. And after I go through all the pre-processing step, and I come up with this kind of radar image, which is one time, again, like one temporal space on one time to the image. But normally, as I said in the beginning of my presentation, I'm going to show you the crop type. So crop type is normally like it is normally captured by using the phenology, because the crop growth is like more of phenomenal. So to catch this, we need this kind of data, which is taken across time. Now we have 4D image. So from the 4D image, for example, when we take a single pixel location X, Y, we will have this kind of crop profile. That means the scattering characteristics of specific pixel at a specific location. And then to train our model, if we have a sample from the field, and we will have this kind of crop-specific temporal profiles. And then later on, we can ingest into this one into deep learning model, and we will have a crop type map. And then what I want to speak here is when we say preparing data for the model input output, the first thing we should note is what kind of model we have, what kind of task we are going to do. As for example, if we are going to do scene classification from tiles, its input output structure is completely different. If we are going to do that classification or semantic segmentation, again, the input is completely different. And then if we are going to do any sort of object detection, that means only we are detecting whether what kind of object is it and what is its localization. And then this is completely different. And again, if we are going to work on instance segmentation, where each individual object will have its own instance, and then the input-output structure is completely different. So bear in mind that if you are going to work on deep learning in Earth observation data, we should first know our data type, what kind of data we have, what kind of model we have, and what is our objective and what we are going to achieve at the end of the day. And that's which determines the data pre-processing. For a specific task I'm going to present, because I have this type of data, and then this type of data has rows, columns, features. That means like VV, VH, and cross intro, and I mean the ratio bands. And then I have 3 bands, and then I have 12 C's, 12 men's, and then I have some amount of rows and pixels. So to ingest this data directly into recurrent neural network, which is a deep network which working on time series data, I should convert it into N. That means N is like provided as a number of rows and columns, which is converted into 2D, 1D. And then T is time of observations, that is sequence length in terms of the recurrent neural network community terminology. And F is the number of features, which is 3 for me right now. Once we pre-process our data, once we converted our pre-processed data into model input-output, the following task is exploring whether we have a GPU in our computing environment. I mean, Python is not going to show you whether you have a GPU or not, but because if you directly start computing without like specifying your GPU, normally the Python is going to compute on CPU. The first thing is you can import Torch, or if you are working on TensorFlow or Keras, again, almost the functionality is almost the same, and you can also see the documentation. That's also, but bear in mind that this, I mean, packages are not directly using a GPU unless they are specified. To do that, you can check the availability of the device, how many GPUs will you have, what is the default current device, or if you want to implement other device-specific tasks, you can also see device name and device properties like this. For example, this demo is done on NVIDIA RTX A6000, which is the latest machine. After doing that, you should also put your tensor or pre-processed image into the GPU by using tensor.cuda or tensor2 device if you have specific device name. And after that, again, you can check whether your model or your tensors, your arrays are on GPU. And when you run this thing, it tells you whether true or false. And then let's build small vanilla network. The first thing when we are building the model is we should first import the necessary packages, as I said. And then once we have the necessary package, we will build the model. When we build a model, of course, again, models are quite diverse, quite many. And then, but the general framework is we should have some layers, neural convolutional layers or LSTM layers, which can compute the task. And then we will have backward and forward pass when we are optimizing the models. For my task, which is for a recurrent neural network, I specified like my input size is like 4 and then hidden layer is 20, and I have a sequence length of 12 because I take it monthly data. And then I built, I specified my LSTM layer here, and then I specify the forward pass because the backward pass is specified during the optimization. Once we have a model, we should put our model like this. We define our model, specify our optimizer, because there are, again, many optimizers with its limits, potentials. I'm not going to discuss that in detail right now. You should specify the loss function and then put your loss function in the model into CUDA as you are quite sure you have a CUDA in your or GPU in your computing environment. And then the remaining thing is building the data set and the data loader object. These are optional. People who are good enough in programming can craft by themselves. It's not mandatory. And then the training process. In the training process, which I want to focus is, please don't forget putting your arrays into CUDA. Once you put your model in CUDA or in GPU, don't forget putting your labels and arrays into the CUDA. And then don't forget putting your optimizer and the loss function in the training process, as you can see in the highlighted section. And here, what I want again to emphasize is at every forward pass, you should clear your accumulated gradients. And then, because if it is accumulated, sometimes when it explodes the memory, the other thing is it gives you wrong computational results. So once we train a model, the rest thing is like, I don't want to go through detail, and you don't forget inspecting the performance of the model during the training. And this can be done by inspecting the training and validation loss. As you can see, it's not bad. As you can see, the loss is decreasing across the epochs. And then the accuracy during the training and validation is increasing, which is a normal trend, but it looks a little bit noisy because it's in the radar data. And then after doing validation, and if you are sure enough, if you are satisfied by the validation results, you can test your model, and then you can create the confusion matrix, which is more easy to understand where the model is working and how the omission and commission errors are introduced during the training. And then if you need, you can also generate the more user-friendly tables on the Python environment. Saying this, you can see here you have a 2D image. It looks like noisy, but it's because of a little bit larger area. So if we zoom in from the smaller area, so the model gives a more vivid result, even though there are some noisy stuff at some parcels, but still this is quite normal because there might be moisture or some confusion in the plot, but still it looks quite nice. After this demo, what I am going to speak is how we can optimize, because having this GPU or CPU does not always entail we are computing in a more efficient way, because still, even though GPUs are fast enough, in terms of their size, capacity, and speed, they are very limited. So how can we efficiently use, or how can we optimize the existing resources? So I may use the speed. I may need the speed. Others may need the storage, or others may need the computing power. And again, bear in mind that the resource may come in the form of standard or local computer, or high performance cluster environment, or virtual machines, as one of the presented by Marcin in the CloudFerro, CREODIAS. So for this optimization strategy, we are also completely different. One thing which looks a little bit masked from the common literature is like in Earth observation, like we may not always need GPU, because majority of tasks is done on pre-processing phase. You start from atmospheric correction, geometric correction, feature extraction, blah blah, and later on you come to the you come to deep learning. So a huge task is on pre-processing, and these pre-processing tasks may not be optimized in the GPUs. In this time, the only option we have is looking CPUs and optimizing the existing CPUs. If you are coding in Python, for example, my silly small computer has almost 8 CPUs. As you can see, that means 8 processors. But if I use the Python processing in a normal way, in a classical way, I am only using my single CPU. And the rest, 7 CPUs are idle, or just running some small system tasks. So how can I use all existing CPUs is the question. So to do that, we should come up with how can we bypass the Python global interpreter lock. To do that, nowadays there are specialized packages, Python packages, which are very useful to do multiprocessing on CPUs. For example, multiprocessing, a package called multiprocessing and joblib are on the market now. So if you have an interest, you can go through in the internet. They have ample amount of documentation. And in the pre-processing phase, you may work on array processing. So if you are working on array processing, the first thing, rather than looking for high performance computing, is try to use existing array processing packages, native array processing package like PyTorch. And for example, PyTorch or NumPy, these guys are very efficient in processing arrays if you are computing on array. As you can see, for example, to compute the mean variance in standard deviation for an image with 500 pixels by 500 pixels, but for 144 days observation, it will take almost less than a second. So which is quite nice. But sometimes we may encounter a problem because we may not directly use this built-in array processing package or functions. So we may be forced to use like if loops or for loops or while loops, which are recursive, memory consuming and slower in speed. In that case, for example, if you see in that case, like if you do in this case, it took almost 21 minutes. You see how different it is if we are working on if loops and or while loops. If you are challenged by this, the other option is try to use vectorization strategy. So vectorization by nature on arrays is quite efficient as far as your arrays is not very huge. And as you can see, the vectorization reduces the time needed to process. But again, this may not always work because sometimes you may come up with huge chunk of arrays. Maybe sometimes you may work on regional data sets and global data sets. So in this time, it's better to use specialized libraries like joblib and multiprocessing. Here, I don't want to not use that. If you are working on joblib and multiprocessing, please try to balance the overhead, because if your data set is small enough, multiprocessing and joblib packages may not give you efficient speed boosting, because sometimes copying data from the hard disk or local drive to the CPU and returning the results into the hard disk by itself is lengthy and time consuming. So again, don't forget balancing these things. So in a normal training process, if we are working on a single GPU, this is a normal training process. You have a model, you have a training loop, you already defined your model, loss function, your device, you have only a single device. In this case, either your data may not fit to your GPU, or your model by itself may have large amount of parameters, and in case it may not fit to your GPU. In that case, there are strategies what we can boost and increase speed plus efficiently use the GPU. The first one is focused on data types and which use less memory. The other type is data input output strategies, and the rest is I can say auxiliary strategies which can serve as boosting strategy. From the data type strategies is currently in the market is automatic mixed precision training. Normally, if you are computing in 64 or 32-bit computing environment, arrays are converted into 32-bit. That's a bit memory consuming. But if you are using automatic mixed precision for your training in the model, it reduces the memory usage by half, and it increases the speed almost by 1.5 or something stuff. And I will show you the graph, which is done by NVIDIA when they are introducing the method. So big thing is not needed. The only thing is like specifying 3 or 4 lines of code inside your looping. And then bear in mind that when you are using automatic missile precision training, the output from the loop should be scaled back to 32-bit, because sometimes it gives you an error, or sometimes the results are the numbers are very small and may not representative. So don't forget scaling back to the normal 32 bits. And this is you can see from the NVIDIA website. If we use speed, it's quite, here you can see up to 4 almost 5 something, and here the maximum speed up is almost 2 point something, which is by half. And even for the larger deep learning models, BERT and transformers. The other is data input output structure, because when we specify the data loaders, don't forget putting the moderate size of the batch size, because if we put batch size, yeah, the speed is quite okay, plus maybe sometimes smaller, but it's not going to consume too much memory. So again, speed plus memory should be optimized in that way. And then specify number of workers which can serve for a single GPU. And again, pinning the memory to synchronize the data input output structure can increase the memory, but again, with trade-offs on the speed. And if we have multiple GPU, as Martin introduced in the start of the training, now they are providing like the GPU flavors on virtual machines, either single GPU or multiple GPU. If you are doing multiple GPU training, either you can parallelize your data, as I can show you here. That means you can put a chunk of data on all GPUs and then you start training by sending your model to them. Or you can do model parallelism. That means you can put assign some part of the model for each GPU, and then doing the training process. And as I see here, as you can see here from here where it's blinking, the model is the forward pass is partitioned into GPUs with their ID from 0 to 4. That means the model computation process is done on distributed and GPUs. And there is also other strategy if you are working on like distributed nodes. That means if your computers are distributed across network, and then all computers have their own GPUs, there's also other strategy which I am not going to speak with a time limit. And this is what I have for today. And thank you for your attention.
Thank you very much. And if you're interested, please join our other webinars. And hopefully see you soon.
Thank you, Marcin, for the opportunity to present in this series of webinars. Thank you.
Yeah, thank you very much. And thank you guys for the presentation. It was really nice to hear it. And I hope we can do another session when we will jump even more inside into the Earth observation and artificial intelligence.
Yeah, that's true.
Okay. Thank you, everyone. See you soon.
Thank you so much. Have a nice evening.